Artificial intelligence, or AI, has come a long way in recent years, with incredible breakthroughs in fields like natural language processing, image recognition, and even game playing. However, despite its many impressive accomplishments, even the most advanced AI systems can't solve all problems. In this video, we'll explore some of the limitations of modern AI technology and the challenges researchers and developers face as they work to create smarter, more sophisticated systems. From the limits of data and algorithmic bias to the unpredictable nature of human behavior, we'll delve into the complex and evolving world of AI and what it means for the future of technology and society. So join us as we dive into the exciting world of AI and discover what it can and cannot do. But before we get started, please make sure to subscribe and hit the bell icon to be notified about our amazing upcoming informative videos. Now sit back, relax, and let's go. Empowered by artificial intelligence technologies, computers today can engage in convincing conversations with people, compose songs, paint paintings, play chess, and go and diagnose diseases, to name just a few examples of their technological prowess. These successes could be taken to indicate that computation has no limits. To see if that's the case, it's important to understand what makes a computer powerful. There are two aspects to a computer's power: the number of operations its hardware can execute per second and the efficiency of the algorithms it runs. Algorithms, basically sets of instructions, are written by humans and translated into a sequence of operations that computer hardware can execute. Even if a computer's speed could reach the physical limit, computational hurdles remain due to the limits of algorithms. These hurdles include problems that are impossible for computers to solve and problems that are theoretically solvable but in practice are beyond the capabilities of even the most powerful versions of today's computers. Mathematicians and computer scientists attempt to determine whether a problem is solvable by trying them out on an imaginary machine. An imaginary computing machine. The modern notion of an algorithm, known as a Turing machine, was formulated in 1936 by British mathematician Alan Turing. It's an imaginary device that imitates how arithmetic calculations are carried out with a pencil on paper. The Turing machine is the template all computers today are based on. To accommodate computations that would need more paper if done manually, the supply of imaginary paper in a Turing machine is assumed to be unlimited. This is equivalent to an imaginary limitless ribbon or tape of squares, each of which is either blank or contains one symbol. The machine is controlled by a finite set of rules and starts on an initial sequence of symbols on the tape. The operations the machine can carry out are moving to a neighboring square, erasing a symbol, and writing a symbol on a blank square. The machine computes by carrying out a sequence of these operations. When the machine finishes or halts, the symbols remaining on the tape are the output or result. Computing is often about decisions with yes or no answers. By analogy, a medical test checks if a patient's specimen has a certain disease indicator. The instance, represented in a Turing machine in digital form, is the initial sequence of symbols. A problem is considered solvable if a Turing machine halts for every instance, whether positive or negative, and correctly determines which answer the instance yields. Not every problem can be solved. Many problems are solvable using a Turing machine and therefore can be solved on a computer, while many others are not. For example, the domino problem, a variation of the tiling problem formulated by Chinese-American mathematician Hao Wang in 1961, is not solvable. The task is to use a set of dominoes to cover an entire grid and, following the rules of most dominoes games, matching the number of pips on the ends of abutting dominoes. It turns out that there is no algorithm that can start with a set of dominoes and determine whether or not the set will completely cover the grid. Keeping it reasonable. A number of solvable problems can be solved by algorithms that halt in a reasonable amount of time. These polynomial time algorithms are efficient algorithms, meaning it's practical to use computers to solve instances of them. Thousands of other solvable problems are not known to have polynomial time algorithms, despite ongoing intensive efforts to find such algorithms. These include the traveling salesman problem. The traveling salesman problem asks whether a set of points with some points directly connected, called a graph, has a path that starts from any point and goes through every other point exactly once. Imagine that a salesman wants to find a route that passes all households in a neighborhood exactly once and returns to the starting point. These problems, called NP-complete, were independently formulated and shown to exist in the early 1970s by two computer scientists, American-Canadian Stephen Cook and Ukrainian-American Leonid Levin. Cook, whose work came first, was awarded the 1982 Turing Award, the highest in computer science, for this work. Beyond Turing. Could there be a new form of computation beyond Turing's framework? In 1982, American physicist Richard Feynman, a Nobel laureate, put forward the idea of computation based on quantum mechanics. In 1995, Peter Shor, an American applied mathematician, presented a quantum algorithm to factor integers in polynomial time. Mathematicians believe that this is unsolvable by polynomial time algorithms in Turing's framework. Factoring an integer means finding a smaller integer greater than 1 that can divide the integer. For example, the integer 688,826,081 is divisible by a smaller integer 25,253, because 688,826,081 is equal to 25,253 x 27,277. A major algorithm called the RSA algorithm, widely used in securing network communications, is based on the computational difficulty of factoring large integers. Shor's result suggests that quantum computing, should it become a reality, will change the landscape of cybersecurity. Can a full-fledged quantum computer be built to factor integers and solve other problems? Some scientists believe it can be. Several groups of scientists around the world are working to build one, and some have already built small-scale quantum computers. Nevertheless, like all novel technologies invented before, issues with quantum computation are almost certain to arise that would impose new limits. And that concludes our exploration of the limitations of even advanced AI. While artificial intelligence has made incredible strides in recent years, it's important to remember that it is still a relatively young technology with many challenges yet to overcome. From issues with data quality and availability to the inherent limitations of machine learning algorithms, there are many obstacles that must be addressed before AI can reach its full potential.